Hooty-hoo! Okay, so, polarity. We've already talked about electronegativity, and we've talked about bonds. Well, a bond is a shared pair of electrons, two electrons that are shared between two atoms. Electronegativity means that each of those atoms wants the electrons, but we already know that electronegativity isn't equal between different elements. Some elements want those electrons more. So when you have two atoms sharing electrons, and one of them has a higher electronegativity than the other, the electrons will spend more time hanging around the more electronegative elements. So we can look, for example, at oxygen. Elemental oxygen is two oxygen atoms bound together with a double bond. Now, because oxygen is the exact same thing as oxygen, there is no electronegativity difference between these two. Okay? So the electrons are shared perfectly equally. Whereas, if you look at water, here's the structure of water. Oxygen is more electronegative than hydrogen. So, okay, let's go ahead. This is non-polar for molecular oxygen, but for water, water is what's called polar. Okay, that's because if you look at it, okay, the electrons for each of those bonds, for both of those bonds, spend more time hanging around over on oxygen than they do over on hydrogen. So oxygen is no longer neutral because the electrons are shared perfectly between these guys over here. The oxygens over for molecular oxygen are neutral, but over on water, the oxygen is partly negative. This right here, that squiggly thing, it's a fancy letter D. You'll recall from that first homework assignment that the Greek letter delta means change or difference. A lowercase d, if you're looking at the calculus, if you're looking at calculus, represents the change in x, change in y sort of thing. So there are lots and lots of different forms of the letter delta to talk about different scenarios and situations. And we use this form of the letter D, a fancy sort of squiggly thing, to talk about what's known as a partial charge, somewhere between 0 and 1. Okay? So oxygen is negative, but it's not, a full negative charge. It hasn't, completely stolen an electron. Likewise, hydrogen has a partial positive charge. So the water molecule is polar. But then you can look at, let's see, I believe my third example on here, yes, oxygen difluoride, OF. Let's go ahead and draw it. It's going to have a similar structure to water, except with non-bonding pairs on the fluorines. Now this time, oxygen is less electronegative and fluorine is more electronegative. So fluorine will hog the electrons, and fluorine will have a partial negative charge, whereas oxygen will have a partial positive charge. Okay? So this molecule is likewise polar. Okay? So a nonpolar molecule is one where you don't have that imbalance of charges. It's actually slightly more complicated than that. We will be getting into that more complex situation after we spend some time talking about molecular geometry. We've already discussed partial charges. So now we have to look at the whole molecule. Okay? This is why the geometry is going to get important. There's a reason I've been drawing these molecules like this specifically, because water actually does have this bent shape, okay? And so would oxygen difluoride, if oxygen difluoride actually exists. I don't know if it does. And molecular oxygen over here on the left actually does have that straight line shape. It can't have any other shape. It's just two molecules attached to each other. Whereas when you look at carbon dioxide has a straight line shape. Okay, so that's why molecular geometry is going to matter, because you can look at the entire molecule and not just the sharing between individual atoms. Okay, the sharing between individual atoms is easy enough to do. You just compare the electronegativity of each element. Here oxygen is more electronegative, so it's negative. Here oxygen is less electronegative, so it's going to be positive. Right? You look at carbon dioxide. Well, carbon is less electronegative than oxygen, so carbon has a partial positive charge, and each oxygen has a partial negative charge. But carbon dioxide as a whole is nonpolar. Okay, the reason for that is that carbon dioxide has this straight line shape. It's linear, as it's known. Linear because it's in a line. Okay, so what you do to represent that is you can just you can represent the what's known as the dipole moment. Okay, that's when you draw a line like this with an arrow. Okay, so you see a plus sign over top the positive atom, and then the arrow points at the negative atom, and then you have the exact same arrow pointing to the left toward the other oxygen. So this right here is a polar bond. This right here represents the dipole moment, and that's a rather fancy term. It's actually possible to calculate a dipole moment. It's the separation of charge, how much charge is on each of these atoms, multiplied by the distance, let's say that they usually call r, in between the two atoms. Okay? So it's an actual number, but we usually don't do that. We can just represent them with these sort of theoretical arrows. Okay? But the thing is, you see these arrows, you can think of them as being, a pull, in that direction. The oxygen is pulling on the electrons, pulling them toward itself. And this oxygen over here on the left is pulling it to the left. This oxygen here on the right is pulling it to the right. Okay? So you have these two polar bonds, okay? And they're pulling in opposite directions. Now, it's a perfectly matched tug of war. So, as a result of being perfectly matched, the molecule is nonpolar, but the individual bonds are polar. That's why we need to learn about geometry, so we can understand things like that in a more concrete fashion, so that you don't just have to take my word for it that a molecule has a certain shape. You will actually be able to predict the shape of the molecule. And here is a fancy, super duper awesome flowchart I made to help you through that. What you do is you draw the molecule and you ask, does it have polar bonds? The way you tell that is, are the atoms on either side of the bond different elements? If no, then the bond is nonpolar. If yes, then the bond is going to be polar. Okay. The next question is, are they symmetrical? Okay. That is the one where you're going to need to learn geometry to be able to answer the question. Okay. Symmetry means that things are nice and even. Okay. So over here, up top, the water and the oxygen difluoride, they have a broken symmetry. Okay, because the hydrogens and the fluorines are actually down to one side. It's a bent molecule. Okay, so it's asymmetrical in one direction. Okay, so that is why these molecules are both polar. Whereas down here at the bottom, The carbon dioxide does not have that broken symmetry. Okay, it is a nicely symmetric molecule. So it is a non-polar molecule, even though it has polar bonds. Excuse me. So if the molecule is symmetrical, then it's going to be non-polar. If the molecule is asymmetrical, there should be a no written. Oops, there should be a no written here, and there should be a yes written here. So if it is symmetrical, then it is non-polar. If it is asymmetric, then it is polar. All right. And like I said, we'll be getting more into that later. Okay. Before we get into formal charge, let me see how much time I have. I have 4 minutes. That's enough time to get a decent start on formal charge. Formal charge is how you judge the correct Lewis structure. What you do is you compare the number of electrons in the bonded atom. You do this for all the atoms in your molecule, and you compare the number of electrons in the bonded atom with the number of valence electrons that it started with. Okay. And how many electrons does the bonded atom have? It's all of its non-bonding electrons, and then 1 electron from each bond. So then you just take the valence electrons, you subtract the bonded electrons, and that gives you your formal charge. So let us look at a couple of quick examples. Here is oxygen with its proper structure. Okay, each oxygen starts with 6 valence electrons, and we're going to subtract the number of electrons that it sees as a bonded atom. Okay, so over here on the left we have 2 from each non-bonding pair, and then 1 from each bond. Okay, because remember, the bonded electrons are shared with the other atom. Okay, so that's 1, 2, 3, 4, 5, 6. Okay, so 6 minus 6, oxygen has a formal charge of 0. Okay, and that's what you would definitely expect for the pure element. Okay, when it's all by itself, it's going to be as happy as it can possibly be. The only time you're going to see aberrant or non-zero formal charges is if you have different elements bound in the thing. Now, that doesn't mean you will have non-zero formal charges. Okay? So let's take a look at ammonia. Okay, recall ammonia has that non-bonding pair and 3 hydrogens. Okay? So each hydrogen it started with 1, and now it sees a single bond, and that's it. So 1 minus 1 is 0, minus 1 is 0. Remember, you have to check every atom, but sometimes it's easy. And then nitrogen starts with 5. Nitrogen, if you look at the periodic table, nitrogen has a valence of 1, 2, 3, 4, 5. And here we see 2 from the non-bonding pair and 1, 1, 1 from each bond. So it has a total of 5. So 0. Okay. So formal charge, okay, that your first rule is minimize formal charge. Get it as close to 0 as possible. Okay. So ammonia is another very happy molecule. Similarly, water. Okay. Hydrogen starts with 1, has 1, 0, 1 minus 1 is 0. Oxygen, 2, 4, 5, 6. 6 minus 6 equals 0. Okay. So, like I said, there's a reason oxygen likes to form 2 bonds. Okay, it's because it has 2 non-bonding pairs and 2 bonds. So a total of 6 bonded electrons, or a formal charge of 0. Okay. Nitrogen likes to form 3 bonds because that way it has a non-bonding pair. 3 bonds gives it a formal charge of 0. So a formal charge is a way of explaining the patterns we see and letting us make predictions about future behavior. Okay. So now let's look at a more difficult case. Okay. Let's look at the dinitrogen monoxide we saw earlier and how it was that I could predict which of those multiple structures it was. Okay, so, run out of time. I'm going to go ahead and finish dinitrogen monoxide. And then next time we'll come back with another example before we move on. So dinitrogen monoxide is either NNO with a triple bond and a single bond, NNO with two double bonds, or NNO with a single bond and a triple bond. Let's go ahead and put them here. I prefer them like that. Okay, so nitrogen has 5 valence electrons and oxygen has 6. So that's the number we get to start with. Okay, now we count the valence electrons that each, or not the valence, but the bonded electrons around each atom. So this nitrogen here has 2, 3, 4, 5. Giving it a formal charge of 0. This nitrogen has 1, 2, 3, 4, giving it a formal charge of +1. And this oxygen has 2, 4, 6, 7, giving it a formal charge of -1. All right, I'm going to tell you right now that having multiple, different charges next to each other like that, not really happy. But these charges are all fairly small. 1 is better than, say, 2. Okay. So let's keep going. So 2, 4, 5, 6. This guy has a formal charge of -1. This one still only sees 4 bonds, 1, 2, 3, 4. So it only sees 4 electrons, giving it a formal charge of +1. And this oxygen has 2, 4, 5, 6. Giving it a formal charge of 0. Okay. Now, we can right off the bat, well, no, let's keep going. All right, so this nitrogen here still sees 4 bonds, so 5 minus 4 is +1. This nitrogen sees 2, 4, 6, 7, -2. And this oxygen sees 2, 3, 4, 5, giving it a formal charge of +1. Okay. Now, the first thing is that the formal charges have to add up to the total charge of the molecule. And that's just right off the bat. So you can judge these, see if you've made any mistakes in any of these potential Lewis structures by just looking at the sum of the formal charges. 0 plus 1 minus 1 equals 0. -1 plus 1 plus 0 equals 0. -2 plus 1 plus 1 equals 0. Okay, so they all add up to 0. The charge on this guy is 0, so no mistakes there. I'm awesome. Okay. And now we can compare the different structures. Okay, this one over here on the right has a whole lot of non-zero charges, and it has a -2. Okay, so this one is just awful. It's crap. It's garbage. Forget about it. Okay, you're not going to do that. So the other two, though, each have a 0, a -1, and a +1. So the size of the numbers doesn't help us there. Instead, you have to look at the differences between the two in terms of where the numbers are. And where the numbers are, here you have a -1 on oxygen, and down here at the bottom you have -1 on nitrogen. If at all possible, put negative charges on the more electronegative element. Okay? The more electronegative element is oxygen, so that means that this one down here is not the good one, and the correct structure is this one up top, which I'm pretty sure I did not say last time we looked at this. I'm pretty sure I got it wrong last time. That's why you should always show your work and check your work, because it's easy to screw up, even if you are as wonderful and awesome as I am. Okay. Next time we'll come back with another example of doing formal charges before we move on.